So, hi everyone. Today I wanted to try to build a version a new version of a static graph, which is a package from the LightGraphs organization. And what it basically does is create a graph which has a fixed number of edges and a fixed number of vertices, which is somehow constraining, but with this it can be represented in memory way more efficiently. One drawback with this is that the fixed number of edges is really a huge constraint, because not being able to remove or add a new edge to the graph, well, it makes it way less useful. In comparison, in LightGraph you have a simple graph type, which is easier to use, so you can modify, remove edges, remove vertices, but it's using adjacency lists, which are all of dynamic size, so it's heap allocated arrays all the way through. One thing I wanted to do is build a compromise between the two and say, what if we have a graph which has a fixed number of vertices but a varying number of edges? And so we can use a fixed size array, which is more efficient in memory and to represent the vertices, but then each adjacency list inside is itself dynamic. Alright, let's dig into that. So we'll start a project from scratch. Templates. Yes. Alright, it sounds fine. Defaults, yes. Oops, no, I don't have plugins. Alright. Generate template, and we call it, how do we call it? Semi-static graph or VertexStaticGraphs. Yeah, we'll leave a plural here because we'll call VertexStaticGraph our type itself. Or maybe VStaticGraph might be a bit shorter to use. Alright, so it's generating the whole thing, and VertexStaticGraph, and from here let's launch code. I might use my terminal editor directly, but also Visual Studio Code. Alright, so we have the code here. We'll just directly create a new file which will contain this static graph. Alright, so you cannot find it. One nice thing about Visual Studio Code and the Visual Studio extension is it has way more, let's say, warnings. Let's say static warning. It's not static, but it's giving you way more information about what's going on compared to let's say Atom, or even worse with a plain editor. So static graph. Yes. Alright, you can now find it. Static graph, right? Same name. Or did I typo it? No, should be good. Alright, so we create a struct here, which would be static graph, parameterized by a type t, which would be an integer type, and it's going to be a LightGraph, not abstract graph. Of course, I need to import LightGraph here. LightGraphs and constant equal LightGraph. That should be fine. Alright. Oops. Oh no, yeah. We need to try to do all the package operations in my terminal. And let's so let's activate this project and add LightGraph and static arrays. Oops, no. Alright. So this should now be fine. And we're also going to use static arrays. And for now, I'll use a blanket using for this. Maybe we'll modify it later to specify what we're using exactly. All right. So one thing we can do here is basically copy the code from LightGraph itself, because, well, we're not going to do much different. Let's put that there. I have LightGraph here. Yes. Let's get the last version of it, and then so there's the simple graph subpackage with simple graph. All right, and it's fairly simple in the number of elements it has. So we have basically the number. Let's put that a bit smaller and zoom in a bit. Yes, that's better. Yeah. Okay, better. So what we have here is, so did I copy the whole thing? Yes, I should not have. All right. So number of edges, okay, and then the list is a vector of t. Which is giving you for at the index source, giving you all the destinations possible. All right. So here, another thing that we will add is the number of vertices will be a type parameter of the graph. And that's something we can do. So what the type parameter will not be a type itself, it will be a value, which will be an integer. All right. So do we need the number of edges? Yes, we also keep track of that. And the adjacency list, I don't know why there's an F here. Oh, yeah. We'll leave the F for the convention. This would be a S vector, which is from static arrays, I think. Static arrays. Do you need static vector or where's my other terminal? Do we need S vector or do we need static vector? I'm never sure. Okay, so what is static vector? Top union all, okay. Let's see. It doesn't have documentation. I think this is the super type. Yes. What if we edit this? Nope. No. No. Okay, so we use S vector. Alright, so S vector st construct construct a statically sized vector of size s. Okay, so the size comes first. S vector, so the size will be n, and the elements inside will be vector t. Yes, vector t. So it's also going to be source to a destination. Yeah. I'm going to try to keep track of a function S vector of a function I'm using. So, and the constructor will be VStaticGraph tn. We don't know, we don't need that. This should just be a type constraint here. Okay, so I don't think we need any additional. Yeah, I think we need the end at compile time, so we will not use. Oh wait, we don't need that end here. All right. Should we add a constructor with just? So the constructor will be. If we add one with val n, for example, or n equal, so this would be this one. This with 0 and the adjacency list. How do we get that? It's not even initialized. That's somehow surprising. No, it's okay. It's passing it the adjacency list already formed. And where is it actually initialized? Here, I guess. Yes, something like that. So it would be, let's put that on new line. So created with T and N, 0 here, and the list will be something like that. But here we are going to use another convenience, which is, I think, at sVector. Let's see. sVector, yes. So this is a convenience macro to create oh, it's not even documented. How? sVector. Yes. So this convenience macro is creating an sVector from a comprehension. So here this will be I feel we can just put it there. No, it's Tn. Yeah, this should be the principal constructor. We'll just put it inside afterwards, and it's accepting just val and yeah. No, yeah, this should be a secondary constructor. So a Tn. Okay, so we don't need that here. Tn. So the adjacency list is an sVector of vector t, okay, for in so we're going to use one. One n. I hope this works. So we're initializing the vector empty, and we won't be able to change the pointer to this vector. It's always going to be the same, but we can change the inside, because the inside will be a standard vector, so it can be grown or removed elements and so on. All right. Between this vector and with the list here. All right. Should we add some tests? I guess it's a good moment to do that. Oh, perfect. We have some run tests there. So v static graph. Okay. What test can we add? Well, first, constructing. I guess this test set will just be don't throw errors. So graph will be a static graph of type. So it's int, and let's say 6, and it's created with length of g.fedge list is 0. I'll just the list is empty, and then this NE equals 0. Okay. All right. So do these test pass. Nope, already a mistake. And not defined. VertexStaticGraphs 7. TN or TN. Did I miss something? Can I create, if we have a T and an N, I'm not sure about the syntax there. So let's see, we have 16. Int. Can I do that? Yes, I can, definitely. Alright. So I guess we need it here, a constructor, yeah, maybe. Function, oops. So this is taking the NE and the fetch list and returning new TN. Okay, oops. Control Q is extremely vicious on this editor. Oops, yeah, there we go. Close that. Alright. Let's rerun the test. I have no idea. Maybe this was done. Nope, still not. Like 10. Well, we are defining it here. Where T, where N. That. Did I type? I'm feeling a typo somewhere. Not defined. Let's see if I do that. Okay. And now, wait, now it works. Okay, so what does it want? It might be here in my constructor. Can I call it like this? Dimension mismatch. it's because I've defined something called n already. This is a bit corrupt here. It might need an n here already defined, but n is defined there. Do I need to manually create my static vector? Yes, because, okay, I get it. This macro is evaluated at compile time, so it's evaluating at compile time this thing, which means you need n beforehand. I have to create, I think, an S vector with the size and the element before from a tuple or something. This is the very first thing. I'm going to check the documentation for GD arrays, static arrays. So how am I supposed to use it now? Don't start with a benchmark. Range is evaluated at global scope. So this should work. You need but we have a compile time constant, which is n. It's very weird that it doesn't accept it. How do we get there? As vector and t, and we pass it this. I'm not sure it will work. Yep. V static graph not defined. Oh, we didn't have this before, so it's better already. Oh, we didn't export it. Oh, that's perfect. That means our test is now having another error, but an easy one. Let's export that. V static graph. What about now? Cannot convert it to an object of type. Oh, did I use t for a yes, that's not t. It's a vector of t. Alright. And just remove this here. Oh, that's better. Oh no, it's not. It's empty. We're not creating it empty. No, we're creating it with length equals 6, and we have to have all inner lists that should be empty. All right, getting there. Yes, perfect. Okay, we have it built, more or less. Okay, we can now, so we have our type, we have a convenience function, maybe we can create it with also a val n. So val n is basically putting a value at compile time, so putting a value like n in a type parameter of a dummy structure which is val to be able to dispatch on the value n. I don't like this here, so we just get back to net tn. Okay, and this is falling back to this constructor tn with nothing. In the test, we'll just add another one, which would be val 6. We can g2. We can basically redo all the tests. 2, and G2. Okay. This should be fairly straightforward. Okay, perfect. And we doubled our number of tests just to feel better. Okay, so we now have a basic type constructor. I don't think we should take an integer, a runtime, well, the type value, sorry, of type integer, because this would be type unstable. We're getting a value and we're putting it in a type. So switching from runtime to compile time, so it means the type of the graph is not type stable, it slows down things. So we better have an API which is efficient by design and type stable by design. So I guess we're gonna create a new file which will be the interface, so the LightGraph interface. And yep, here. Okay, so we will implement all the fractions from LightGraph. So the necessary one, edges. Did I reevaluate everything? So edges of, so this is an iterator on the edges, or maybe we'll do this one later. NE of G, which is a vertex static graph. Will just be G.NE, so that would be fine. Oh, why is it lost? We validated everything already. Alright. And V is the number of vertices of, so this takes types. So the great thing here is that we don't even need the value G, we just need a type. So if we're getting past something which is of type VStaticGraph Tn or Tn, and by design the number of vertices is n, and we're done. All right. Vertices of something here or Tn equal equal to n. Alright, perfect. Everything's still going fine. I'm just gonna check the interface from LightGraphs itself. Interface. Alright. Abstract edge, we don't need that, we just use simple edges. Is directed. I don't want to create a directed version and non-directed version, so I will just use a type parameter and dispatch on it when needed. So this means I need to modify my type itself. And this will be directed or undirected, because the structure behind is strictly the same. So if we don't pass it anything, okay, we'll create a default one, D, where T and D, and here D will just be a boolean, so it will also be a value just like n, saying true for directed, false for undirected. Now let's see, D, so this means we'll create one more. So we can have one with 3, with the one with 2, let's say, yeah, T will just be false. Okay, and we'll also be able to pass T with n and a second value with parameter D, and this will be T and D. Okay. All right. Once we have this, we'll do this directed of a static graph T and D, where T and D will just be returning D. It should all be fine. Oh, we modified. Oh, new, yeah, that's right. In new, here we also need the type parameter. So this should still be passing now. Nope. The method matching in 60 word D. Don't we have that? Oh no, we don't have a 2 argument one. So it means in the test, should we maybe have one? Maybe. Let's create this one with true. And this one with false. No, yeah. We're not gonna do anything about the interface here. We create a new test set below. And the interface. So this will be undirected graph and DG will be in 6 true. Alright, and then test. Did we here we just use my graph. So NE of G equals 0 equal NE of D. Okay, and then V is a bit to have 6. Then test is directed of G. So G is not directed, but the directed one is. Okay. Nope. And what do we have? No method matching int 6. Did I forget something? Stack trace here. VertexStaticGraph 12. Oh, yeah, indeed. What about now? Good. So the basic first functions of the LightGraph interface are set up. Let's see, what else do we have? Alright. So is directed is done. Source, that's for edges. We don't need that. Edge type, yes, we need that. Edge type of this, yeah, for now I guess we'll just keep equal simple edge. Yeah, we're just returning the type, so yeah, simple edge. It's a concrete type, I think. This type of, oh no. So we need the first parameter because this is the type of integer we're using. So that. Okay. So this is fine. L type of G is T. Okay. Well, there should be a fallback for this. This should be the, because we're parameterizing the abstract type. So it's actually not L type. No, it's base. This is a base function that we're overloading. T is T. And we're done. Still everything passing, no error. So the tests are a bit long because we're just re-resolving, verifying that we don't need any change dependencies or anything. And we're recreating an isolated environment every time. NV and E are done. Vertices, yeah, we did that already. Edges is the tricky one. Edges requires defining a new iterator. For now, we could just use a comprehension, for comprehension, which is a bit brute force, but maybe fine. Or we could even reuse the edge iterator from LightGraph itself. Is directed is done. Has vertex, all right. So has vertex. That has vertex, so it will be our graph. Oh no, we don't even need runtime information here. V, and this will be V in vertices of, no, we need to pass it the graph. G, yes, and this will just be is V in the vertices. Okay. Nope. Has edge. Okay. Now we're getting interesting things. So LG dot has edge. simple graph, static graph, with a source and a destination. And this will be is there an edge from S to D? And the implementation is not the same depending on. Oh no, the implementation is actually the same, because so we don't need the information of are we directed or not. So we just have a list, and then so this is getting the vector of vectors, and each vector is. Oh no, yeah, we'll do things a bit cleanly, because we should not error if we don't have a vertex, for example. So as vertex GS and as vertex GB, or return false. It's a bit long. Let's put it on 2 lines. If return false. Okay. Otherwise, out equal. So we're getting the list, the adjacency list for the source, and then we're checking. Do I have an end? No. And then we're checking. How is it implemented again? Let's check. Let's check simple graph. Simple graph, and then simple graph. Yeah, since we checked if list S is greater than list D is longer, sorry, D equal S. I'm not sure how this is getting stored here. The nasty thing to do will be, do we even need to understand this? Can we just widely copy it and get it working? I'm not really comfortable with the idea. Okay, no, this is just an optimization trick. So getting the 2 lists and then asking, okay, which one is the longer, and I'm just gonna check the shorter of the 2 because it's undirected. But this works only for undirected graph. So I guess we'll just use the 2 implementations. So this one, I'm not sure where insorted is from. Okay, so this only works if for an undirected graph. Return full. Okay, age out of bound. This yeah, we can leave the comments inbounds here. Right, you can use inbound here, and insorted. I'm not sure where it's from. Insorted. Do we have it somewhere here? Yes. That's what I see. Details. But it's still there, so we could just use it from LightGraphs directly. Insorted, okay. Oops, should I have closed that? So G, oh no, sorry, D, okay. So that's not for all of them. So T and D. It's not for all of them. Yeah, I don't need the D here. It's for false. And we don't need D. And then there will be the true one. And so this will here dispatch on the value, which is fairly neat. And here for this one, I closed it. LightGraph. Oh no. We're going to check in the other implementation, which is a directed one. So simple digraph. Oh, is this using the same trick? No, it should be a bit lightly different. List packages, okay. Okay, it's keeping forward adjacency list and backward adjacency list. So we are not keeping that. That's very interesting. I always thought all the functions were almost the same, but the underlying structure is slightly different for the for this one. Let's check how it looks. Where is the structure? Here. Okay, yes. Okay, yeah, it has the forward and the backward adjacency lists. Okay, so now the name makes sense to me. So it has source to destinations and then destination to sources. It's like a sort of cache. No, not a cache. A doubled implementation. A doubled storage of it. Okay. Anyways, it's fairly interesting to know. I didn't know that at all. Make it bigger. Okay. So this was the interesting thing is we didn't add a back adjacency list here for the undirected one. We just have a forward one. So this means return in sorted list and D. Okay. Now we're removing this, so we're slightly less optimized. And oh, it's not. Oh no, yeah, it's now this one. Okay, so we're slightly less optimized. That's something to keep in mind now. But the advantage is that we just need one graph type for the two of them, which is fairly neat. One thing we could do is just have a function back adjacency list which returns either. How could we get that? This will be an abstraction, and a function backward adjacency list on an undirected graph just returns you the forward one, and otherwise you have a proper structure stored. Okay. Anyways, back to the interface. Where was I? Yes, here. So C interface. All right. Back to the interface. What other function do we have to implement? This is all for edges. Vertices we did. Edges is the tricky one. Is directed, yes. has edge. Yeah, that was has edge, so it's fine. In neighbors, okay. Yeah, in and out neighbors. In neighbors of, which is a v-static graph. Should we use a fallback? And v of a vertex v, where t okay. So how do we do that? Let's keep it a bit later. Okay. In neighbors of, so it's strictly the same as out neighbor for a directed one. But for now, so it's basically returning these ones here. So it's the adjacency list. Oh, in neighbors are the one pointing onto you. So it will be the backward, the backlist, let's say. That's why it's keeping a backlist. Interesting. We could have an optional element which is a backlist, and it depends on the fact that you're directed or not, but it sounds fairly tricky already. So this will be only for false for now, so this is the easy case. V, so we're getting the list first. What do we do if returns the reference? We can instruct another copy. Okay, do that modify result, sure. So v vertices of the graph, or return, let's say, an empty list of t. Otherwise, inbounds no, this list. So we have the list of the neighbors. Oh no, we want the in neighbors. Oh, but yeah, for undirected one is the same, so we're fine. And then we'll just return all of them. So inbounds return list. Oh, we should also use, this should be annotated as a bounds check here, so that the inbound can be propagated. Okay, and for the out neighbor, for the undirected case, out neighbors will just fall back to in neighbors. Neighbors of G V. Okay. Is everything still working as we expect? I don't have any typo or anything. We didn't test, so for now. Okay. What's next? Yeah, in and out neighbors now for the directed case. Alright, so in the true case, out neighbors is strictly, we should define it on out neighbors here and have in neighbors. Because here the out neighbor function would be the same for the two of them, so it's fairly practical. So the out neighbor will be this, and it's the same regardless of being directed or not. And for the in neighbors, in neighbors, in the undirected case, we'll just fall back to this, and we don't need that comment here. Oh yeah, we should load this one below, because that's the only thing that depends on directedness. And here, in neighbors for true, we will need this backlist here. Alright, so we have out neighbors being the same, in neighbor. Okay. I think now we'll need to modify the type, so the underlying structure, to store the packages. Otherwise we won't get what we want. So this will be modifying this here. And so we will optionally have package, which will also be, so this will be a type BT for back edge list. So this will be BST, SRC, okay. And then this will be another type parameter here with BT. And BT will be either, we'll document this one, and BT will be either this, or this will be a union of this, another one, or nothing. So at compile time, when getting this, we'll deduce either it's a nothing, or either it's a nothing if the, how to say it, if the graph is not directed, we don't need a package list, we just use the same thing twice. Or if we're directed now, then we'll store it, and this would be this case. So how do we constrain it to have a good thing? We'll just do that here. So here we have the compile time information of, so we'll use one on true. So this would be new true, and then this would be this case. And then here we'll create the package list. We'll just do it like that. This will be the package list. This, oops. So this will be the first case, and the second case, we are not using D, right? We're just using true, okay. And the second case, which is if false, with the list here, and then we'll just return false. This will be nothing, and then there we go with nothing here. Alright, this was, so now we still have the two same constructors, so that's a nice thing. We don't break the other constructors here, but now we have an additional package list which can be nothing, or it can be the actual package list. Great. Now, what we'll do is create a function, or does it even exist? We can maybe override a function that might be already in simple graph. cd. Let's get into this and see if we have a function. Badge. Nope. Do we have it? Nope, either. Edge list. No, really? I thought we had a function for this. Okay. Oh, maybe adjacency list. No, okay, I thought. My bad. So we have a function which would be internal G, which would be VStaticGraph T and true. This will return G dot like list, and then the same thing, but now for false ones or for an undirected one, this will return the forward list because the two are equivalent. Okay, it's a bit of a trick here, but I'm happy with it. And I think now we can implement things correctly. Oh, so where was my to-do fix hack? This LG interface. Oop. Here. So the in neighbors for a directed graph, we'll get the package list. The graph, and on this package list we're just going to process things exactly the same way. First the bound check, then the package list, yeah, we didn't do any bounce check in the package list. No, we don't need to. No. And then list equals the package list of v. Okay, perfect. And this actually works for all in neighbors, because this package function is defined for both, so we don't even need to know if we're directed or not. It should work. I'm pretty sure it doesn't, but we'll see. So in neighbors, wait, what was that? G and V, what am I doing here? Oh no, yeah, so we don't need that anyways. Okay, I'm pretty sure it doesn't work. So out neighbors is defined once. And do we need? I don't think we need two definitions. No, we just need two definitions, and that's pretty wonderful. So one for out neighbor, one for in neighbor. Neat. So did we break something now? Because with this added constructor and so on, with this modified constructor, we might have broken many things. Line 15. Oh, yeah. That's no big deal. Or TN. Oh, no. Or TN. Okay. That should be better. Yes, perfect. Okay, it's even. I'm surprised it works, but we haven't run any tests for a moment. These neighborhoods will be their own test set, because lists and neighbors false true. So test list. So for this should be nothing. This, I don't know how it could be a good idea to have Control Q doing something so radical as closing everything. The Q is just dangerously close to everything I'm always typing. Alright, so this should be nothing, and the directed one should be S vector of something, abstract vector, because we didn't, or we can just test the length. This should be equal to 6. Okay. Let's test that. Good. So we now have the package list abstraction, let's say. So for the, now if we test the package, so this would be VertexStaticGraphs. This will not be exported. Match list of G. We can tell that it equals the forward list. And for the directed one, it should not be the same object. This should be G, and this should be G. Okay. Oh, this is going pretty well. Oh no, this is not a test. Okay, perfect. All right, so we now have the behavior we want, but we didn't test for neighborhood yet. Oh, and for that we will probably need to be able to add some edges to our interface. Implement the interface here for adding edges and so on. Okay, so we have the neighbors. How are we doing on the interface side? No, let's go back one step. Macro interface. So we now have the in and out neighbors, but we cannot test them yet because, well, we can tell that it's empty for now, but I'm not sure it's that useful. Vertices is fine. Edges, we haven't done it yet. Again, is directed. It's fine. Oh, interesting thing. We're supposed to do is directed not on the graph itself, but on the type of graph. Type of any graph that's T and D is D. Okay, perfect. Should still pass. Yes. Alright, what's next? Has vertex is fine, has edge is fine. Oh, we can now re-optimize the has edge, but we'll do that later. In neighbors is done. Out neighbors 2. 0 of the graph. Return the 0 vertex, 0 edge version. Do we? Okay, sure, we can do that. Base of 0 of, it's on the type, right? I think, yes. So we have to define it on the type of static graph, type T and D. Yeah, it's awkward to have the N here because we are saying give me a 0 edge, 0 vertex. But we specify this here, so it means we're just gonna ignore this type there, which is fairly awkward. But yeah, where T and D, because we need the D anyways. And this will create. This will correspond to creating this, and that's it. I don't think we need anything else. What does the constructor say? Yes, let's call this constructor. Oh no, sorry, this would be 0 here, because we're saying we're creating it without anything, which is fairly useless, let's say. Alright, so we have everything in the non-mutating functions, which are in the interface. The mutating functions were split from the interface, and the kind of pain point now is that they're defined not in LightGraph itself, but in the simple graph submodule. It should not be, because we are implementing it even for other graphs. So we should not be implementing it from simple graph, but from LightGraph itself. So I guess we're just going to copy the ones from there. So this is the interface implementation, and then the mutating functions come. We have to be able to create, that can be a useful function. We call it simple graph behavior. No, a simple graph interface. I don't like it, but we'll keep it as is for now. So do that simple. So creating a simple graph from vsafe. No, it's sorry. Static graph can only be done if this is T and false, I think, or Tn. So creating basically a simple graph from our static graph, and then we have a simple digraph like this. I'm not sure. This will be only from the true version. Alright. Simple graph. This is digraph, yes, with the 2 capital letters. Perfect. So this will still be some to do for later for now. Clean up edges. I don't know. No, this sounds like something we should not have. Simple graph from an edge list. Add 2 f edge lists. A simple graph from iterator. No, we don't need that. No, from iterator, we don't need that. I don't think we can even have it, because this is modifying the number of vertices in the end. So we don't know at compile time the number of vertices, and we need that for our graph. Edge type, return the backward adjacency list of the graph. Oh, interesting. Oh, so the function is bh, so we should probably use it. Okay, yes, we'll definitely use an fh. Okay. So this would be the first interesting function, I guess. One thing we'll do now is probably simple graph interface. Yes. Again. Sorry about that. Yeah, there we go. Okay. So the edge here. No, we should not use it here. This should be defined when we define the whole LG interface, because we're using it. And this was, where was our edge list? Where is this one? Yes, here. So it's basically replacing that here. This, and then the forward, the f edge of any v-static graph is just returning f edge list. Perfect. Oh no, I did something wrong. This is supposed to be no, sorry. Oh, what a typo. Okay, no, this is doing the correct thing, obviously. Okay, perfect. Oh, and then edge list. Oh, it's fine. We're not using it anymore. We're supposed to use it somewhere for the neighbors. Ah no, it's here. In there. It's here. Okay. Let's just check that everything still works. Nope. The edge not defined. V-static graph 15. LightGraphs doesn't have a pH function. Interesting. I thought it had. If we're doing this, and no, it will be in simple graph. Simple graphs. Edge. Yes. I guess since it's a fairly long name, we might do better to import it explicitly. Edge. Okay. Because we're overriding this function. And also f edge. Okay. Nope. Vertex doesn't have LG. Oh, okay, no, I can't use. Oh, interesting. I can't use alias for this. It might be worth posting an issue for that. Let's keep that in mind for later. Issue import with alias. For now, we need things a bit more explicit. Where's this one? This. Nope. Still an error. Yeah, it's not defined. It should really be defined. what if I do that? Oh no, yeah, sorry, I now need, not here, but in the whole project, edge.bEdge. Yes. This should be now bEdge. And same thing for fEdge. Alright. I guess we're good to go. Oh, what do we have now? bEdge list. Oh yeah, okay, the test. Of course. Yes. This is now bEdge. So this is LightGraphs, simple graphs. It's bEdge. Oh, did I import with const? With it here. Right, so id.simplegraph.bEdge and same thing below. Alright. We should now be fine with this. So this construct here is fairly neat because I think with this we can just skip all of most of the details repeating themselves between directed and undirected, and we just have very few functions which need to dispatch on the fact that we're directed or not. So that's fairly neat. I'm happy. All right. Add the adjacency list of the matrix. Okay, but I'm not sure we need that. Simple graph. Oh, that's interesting. Maybe we should do the same. But are we? I'm not sure we should compare a list like this. I'm not sure it's an element-wise comparison. If we compare two vectors, I'm not sure this is calling the function we want or not just a pointer. Array, or array union, Okay, no, this is fine for numerical arrays. I don't think this will be the case if we have lists of lists. Tedious to type that. Abstract array. Can we edit it? I might be doing that in the terminal. Yeah. So what does it look like? If x is okay, so this is still a proper comparison, I guess. Any missing false for AB and zip AB equal AB, okay. Okay. Interesting that they don't have an early return of this. Okay, whatever. Anyways, return any missing true. Okay, so it's still using some sensible comparison. Interesting. Today I learned something. All right. So we can use this comparison here. We don't really need that for now. Vertices. All right. I guess we can attack edges soon. Add edge. That's the interesting part. So adding an edge to a graph G and E. So in that case, we can implement either like this or like or with source and destination. I think the interface only specifies with source and destination. So adding an edge. So instead of a simple graph, now it's going to be our v-static graph. Okay, so let's think. If we have an undirected graph, we just need to add an edge to the forward list. If we have a directed one, we also need to add it to the backward list. So this function here will need to dispatch on the directedness here. Okay, perfect. E will be here for now simple graph edge. We can have any edge actually. So it's abstract edge. Yes, or T. So this is in the directed case. So we add the edge first to a list. So src, yes, balance check has edge. G E. If it doesn't have the edge, then this is or return false. Oops. So if it doesn't have the edge, oh no, it doesn't need to have the edge, sorry. It needs to have the vertices. src E, and then destination bst E. Okay. So it has vertex G src return false. Can we have multiple bounds check in a function? I'm not sure. I'm just going to read that here. Bounds. No, sorry. It's a macro. Alright, so what did it say? And the expression as a bound checking block, allowing it to be elided by inbounds. Okay. Inline, okay. We need to inline the functions that have this. Do we need that? Has edge source or return false, has edge destination or return false. And now, so this will be inbounds. G. No. Getting the list is does not inbounds, but list equal f list at vertex source. Right, we need to check if we have the edge already. We don't need to add it again. E, return false. Now we know we don't have the edge, so we can just add inbounds list equals f list And then list, do we keep them sorted? I think we should keep them sorted. Is there insert, sort insert? How does LightGraph do? So getting the vertices, checking that the vertices are in the graph, okay. Getting the lists, sure. Search sorted first. List D. Okay, so this is basically checking that it's already in the graph. Insert list index. Oh, oh, okay. In the search sorted first. Is that the standard Julia function? Search sorted first. Return the index of the first value is greater or equal. Okay. Length a+1 if it's greater. Okay, interesting. So yeah, we can definitely use that. Should we just maybe copy it? Index is smaller than the length of a list, and list index equal D. Okay, so that's the equivalent of has edge. Maybe we should just use that. Yeah, that's great. Oh. Alright, and we're also writing in the other direction, that's in the undirected case. We should maybe check the directed one, but it should be that. So source destination. Yeah, maybe I should have used the shorter name, SND. Insert, okay, that's equal D and return true. This is in the case of a self loop, and otherwise, oh, we didn't. T, we don't need N here, I think. No, yeah, we don't need the N itself, but we need the true, so if this is a self loop, we don't need to insert it to the backlist, or do we? No, we still do. I guess it's fairly dangerous. We just consider undirected case first, which is the one we have under the eyes on the LightGraph side. Okay, self loop here. If it's not a self loop, then we need to insert also from D to S. Inbound, yeah, I guess it just makes sense to just copy everything here. So I'll thank the LightGraph developers for having a nice, having thought everything nicely like this. Okay, so we have our edge added in the undirected case. Now I'm wondering how much we'll need to vary this thing. Yeah, I might have a hack to just write the function once, because it's equivalent to write, in any case we're gonna write from destination to source. If it's undirected, we write it in the forward list twice. If it's directed, we write it from source to destination, the forward list, and from destination to source in the backward list. But the backward list in the undirected case is, alright, I'm just losing myself, so we'll write it, and then we'll try to reduce it to just one function, and we'll see if our tests pass. For that, we'll need to write tests first. So I'll just do the same thing with simple digraph, and and then add edge. Where is it? Here. Nope. Here. Alright, so we're doing basically the same thing. Vertices, bound checking, bounds, and then yeah, inserting in the backlist now. This is really the same function. Oops, no. Just copy the function first. It's almost the same function. Up. Alright, so first thing is, yeah, we have an abstract edge, so instead of SMT like this, we'll reuse source and destination. Source and destination, then vertices is verts, okay, I'll skip that name, it's fine. Did I? Yeah, maybe it's a bit cleaner like that. Oh, that, yeah, we don't need that anymore. Has vertex. Oh, we're not using verts anymore afterwards, so we can just do it like this. So here, instead of flist, we'll edge of the graph. Instead of using the field here, we're just going to use flist. And same thing here, instead of that, it's going to be list edge of G, and then list for backward lists. Alright, so this is, if we unzoom a bit, this is now our undirected version, and this is our, oh yes, directed version, of course. So the two should work. So we're going to test them, and then we're going to try to squish them together. So have just one implementation, because we just have basically the same code. Okay, so let's start again where we were. So the thing we wanted to do now is add tests for this. We are able to add some edges. We are able to test if we have some edges. Yes, we implemented has edge here. Perfect. So this means we'll create a new test set there. This will be edge addition and presence. So we'll again create the directed and undirected version, and this time edge G. Let's say, oh, we only have the add edge. Well, we'll see if this works. I'm not sure this will work because we didn't define it. I'm not sure there's a fallback. So let's see. There might be a fallback in LightGraph for add edge 1, 2, falling back to add edge. Nope, there is none. Yes. This is I prefer using it like this, so maybe we should just define it with source and destination directly, because we don't need anything else. And same thing here. Oops. destination. There we go. Nope, still something. No method at edge. Oh, we did. Oh, we didn't include the file, maybe? Simple graph interface. We did. Oh, yeah, we defined a new method. We didn't override it. I feel like this should be an error somewhere when you are... No, never mind. This will be a bit too complex. But here I was defining a new function which is not the same as the LightGraph one. Them having the same name does not mean they are the same function. You need to use specifically the one from LightGraph and specify that you're using it. Okay. Vertices not defined. Oh, we are iterating over vertices somewhere. We haven't defined it. And where is that? Edge interface 14. G.vertices, perfect, yes. Okay, the next one, VertexStaticGraph, set field, oops. Simple graph 19. Oh, that's a bit of a bummer having to change our structure to a mutable one just for this. I'm not sure it's worth it. I might want to have a reference to a number of edges. So if we create a ref to an integer for the value, can we do that? Yes, or yes, it might be better. Yeah, I would say so. So let's just do that. Because otherwise, is it worth it? Can we just, maybe we should put it as immutable. As mutable, sorry. Alright. It's just sad to have to do it just because of this field here which is being updated. Alright, no, this... I don't think we're losing too much on performance here. Because the rest of the fields are just not moving. Well, they're moving internally, but that's just this one. Anyway, it's a fairly big advantage to be able to define things as immutable, so we can have this type of error, which is nice. Oh, perfect. Nice. So we don't test anything here, but we don't have any errors. So we adding an edge here. Test EF G equals EF G equal 1 will be the first one, and let's add 1 to 3 here. So test out neighbors of G1 equal 1 equal also the out neighbors of G1 equal 1, okay, and then the in neighbors G, so for the directed one and 3 equal 1, and then just to be sure that we didn't revert anything, the out neighbors 3 equal 0, sorry. Alright, we're testing multiple functions here, so there might be some errors. Yes, there we go. Vertices, okay, that's an easy one. Where is that? Edge interface 36. edge interface 36. Oops. We should be using flist here. Fetch.g and flist. Okay, the alt neighbors is a list. It does make sense. Oh, vertex is not defined again. Edge interface 43 now. Yes, same thing. Okay, and now it makes sense. We did a mistake here. So this is returning a list. This is just empty. And so it's the length which is identical here. And the length is 1, okay. So the test which failed were just type errors. I mean, the neighbors are returning lists, not numbers. Okay, perfect. All right, so we are now able to add some edges, which is what we wanted to do. And the tricky function that we wanted to regroup as one was, add edges, okay. So, for now, we have two functions, and what we want is actually squashing them together. So what we'll need is ignoring the directedness. It's the first thing. So we add source to destination in the forward here. If this is a self loop, we just stop. Otherwise, here this will be the backward list equals edge of the graph. We're using the backward list here. And then we are inserting from destination to source in the backward list, which is also the forward list if we're directed. Okay, and so we don't need this one anymore. I hope this works. This will be neat. Let's see. Yes, perfect, it works. So we don't even need two different functions for adding an edge whether the graph is directed or not. So it's a fairly interesting experiment to have. Maybe at some point this could be merged into LightGraph, the simple graph version itself, and that would be nice. All right. So now removing edges, which is more or less the same trick. Oh, one thing I wanted to test if whether we have a fallback for adding an edge when it's the edge itself. Can we add oh, okay, we can also test here. These two are supposed to be true, but yeah, they should be. And then test that this is not the case here, we're not adding it anymore. And same thing for the directed one. Perfect. And now what do we want to do? Yeah, removing edges. Oh no, sorry. Yeah, I'm losing myself. I want to test if we can add an edge, which is now a simple edge. LightGraph simple edge. Or no, edge, just yes, edge from 1 to 4, let's say. And if this also works for I hope this does work. There should be a fallback anyways. If there's none, we should define one at the LightGraph level. Okay, interesting. So this should be a to-do. Fallback. Where did I add? I had a list of things to do for later. Yes, here. Issue alias LightGraph report. So this would be issue with report for fallback, add fallback for add edge GE edge G srcf E and stfe to use open source. All right, perfect. So for now, we'll just leave it as this. So this is test broken and test broken. I'm not sure if broken. Yes, okay. So we're leaving 2 broken tests to remind ourselves that we have to do this later. Alright, now how do we remove some edges? Well, this should be fairly straightforward, almost the same function. Let's give it a try. So it would be the reverse thing where we remove in the forward list from source to destination, in the backward list from destination to source. So it would be run edge. If we don't have a vertex against, we return false. How do they do it now in the we can just short circuit the thing and just call edge as edge GSD or return false. I guess this is what LightGraph will be doing. Let's see. Remove edge out of bound. Oh, so it's the same thing and then delete that. Okay. No, so we're not using this. Delete at list index, and we don't need to the value here. All right. Minus equal 1. So as equal then we're done. Otherwise, get the backlist. Insert. No, we're not inserting now. We're delete at list index. Return true. Deleted. Oh, this inbound thing should not be there. Oh, it's not in graph. So it's index smaller than this and list index equal D. Wait, what? How different is this one from the one we had for edge not in graph? List index equal D. Well then, if that's the case, it is in. I didn't modify this, right? No. I think I need a bit more time to understand this one. Index is smaller than the length of a list. This means it's there and list index equal d, but then it is in the graph. I need some explanation on that. Rem edge. Are we sure? Explanation on rem edge. Okay. So for now, I don't think I'm gonna use this because I don't get how this would be the case. Maybe is it a bug to file? I'm not sure either. So it's select, no, not select, search sorted first. So return the index of the first value in A greater than or equal to X according to a specified order. Return length A plus 1 if X is greater than all the values in A. A is assumed to be sorted. Okay. So if so if the index is smaller than the length of the list, then oh wow, this is tricky. Or return, and here this is n return. So this is checking that the edge is actually not in the graph. Okay, sure, no. This is the or here. Oh wow. Okay, I get my explanation. I guess if you're watching the video, you just like face palming and saying, how did you not see that? Okay, so this is the sanity check that the edge is not in. No, we had that. So we return, so we have it in the graph, or we return false. Sure. And then delete at, because if we're here, it means it's not there. It's still there yet. So we delete it, return true, we get the backward list, and then we delete that list index. Okay, this looks sensible enough. Edge addition and presence. Okay, we'll just do another one for the removal of edge. Rem edge. Rem edge here. This should work, and then test. There should be 0 edge after that, and then this should not work anymore. What thing we should check is also, for example, that there is an out of bound error. Checking vertices bounds does not, so let's say 1 to 7 and 1 to 10. Okay. We'll do the same with removal. Alright. So this should be fine. have edge removal in place, edge addition, add vertex. So this one we don't support, so we don't need to add it. Run vertices, same thing. That's great, less functions for us. And we are finished with graphs. So one thing we could do is use the same test set that we are using in LightGraph. Micro src dominate. Yeah, let's try some random one. Wait, is this in the source or it's in the source? We want to test oops. Could we just no, we don't want the generators. Oh wow, we completely forgot the edge iterator. So what we want, let's try the test first for a change. What we want is to be able to iterate on the edges. It sounds edge iterator. And then what we want is to be able to use the edges functions. So we create as usual graphs, and edges G. So we should be able to test that edge 1, 2. This is not in edges, and then if we add an edge, if we add an edge here, we don't need to test that again. Now want to let's try this in the in-place version. Let's try it in plain way. So edge in edges. So yeah, let's test that. And then edge 1, 3 in edges of the directed one. And then also then edge 3, 1 should not be in the edges of the directed one, but 2, 1 should be in the undirected one. Okay, so this will now fail because we haven't defined the edges iterator function. And after that we'll implement it. Alright, method error or something. Not implemented error. Okay. So for this we'll not use anything smart. We'll just reuse everything from LightGraph itself. So this means it's in simple graph that we have a simple edge iterator. So I hope this works well for iterate. Simple edge iterator. So it has graph G, okay, and the state. So how is it using and that's great. It's using the fetch function, so we might be able to use it directly. Maybe that would be great. I hope it's really not using anything specific from too bad. It's using the abstract simple graph. It's subtyping on the abstract simple graph, which is a bit of a bummer. because we can't use it directly like this. But we can maybe just redefine this iterate function, which will be the same, but for our graph type. That, or we could make our graph type subtype of abstract simple graph, which also works. Yeah, I guess this will be, and then we have the edges function somewhere. So this is doing all the work for us, and then simple graph. Oh, we don't have the edges functions here. Yeah, maybe it's at the top level of the module here. Simple edge there. Okay. Hey, this could actually work. One thing we could do is not subtype in simple editors to be able to reuse it. But I guess the lazy version would be to change the super type of our own graph. So this will be here, and the only thing we need to do is replace that here with abstract simple graph. Let's see what it does. It's playing fairly risky. Worst thing, we can always copy the code, but it's never great to do that for nothing. Oh wow. This vertex is ambiguous. Candidate abstract simple graph. Oh, maybe we don't even need to redefine has vertex. That would be great. Yes. So we now have some functions that we don't need anymore. So has vertex is 1. Well, this is even better news than I expected. Let's reduce this. So it will be here. So vertice, no, is has vertex. We don't need that anymore. One thing we might want to do before all this, since this would be a fairly big change, so it's here, is do a first commit. src first draft working somehow. Okay, now we can break everything. Let's see what we need. So we had an ambiguous method. We could just fix the ambiguity, but we don't need it anymore because lots of things are defined at the simple graph, abstract simple graph level. Method ambiguous, we don't need in neighbors either. Simple graph, but is it what we want exactly? Badge. Oh, we want that, so it means we just keep the definition that we have. B adjacency list and F adjacency. Oh, okay, interesting. So this was for in neighbors and out neighbors. Out neighbors, so integer here, and in neighbors. Okay, so with this we now have a function being specific enough, because there was an ambiguity between two methods for one function, and the multiple dispatch system could not decide which one was the most specific. Oh. I think we now have some proper error to debug, which will be a bit more interesting. Okay, remove edge, method error, edge is ambiguous. Candidates are remove edge in here and in here. Okay, I think we might want to keep our method for this. I'm not sure. We'll check. What is this simple graph form? Remove edge here. Edge type. Okay, this is rebuilding. We now have a fallback. Interesting. Okay, so the fallback is defined at this point. I thought this would have been defined the other way around, like defining with U and V, and then removing the edge with one edge is just removing the edge with the source and the destination. Okay. Well, it's not a big deal. We just need here to oh whoa, what is this one? Simple. Oh, it's a constructor, we don't need them here. Was it for removing the edges only? Yes. This might be a to-do, like consistent fallback between add edge and remove edge. Consistent fallbacks for add edge and run edge. All right. Where were we? Here. Yeah, no, it's remove edge. This one. So this will be defined on E. And this will be SRC on E and DST. Okay, what do we have now? I guess we're gonna get more and more into proper testing. Yes, obviously. We're now, I guess, gonna get more and more into proper test error, so implementation error, because I think I saw some. And let's Stack Overflow, simple edge. This one, okay, we might have, okay, I think we have a fallback in the wrong way. Has edge G equals has edge type G. What do we need then? Edge type. Okay, so we have to define has edge for our edge type. So it will be here. Oh no, okay, we need to define our fallback ourselves, it seems. I'll just try it. Oops. Edge. The fallback system might be a bit tricky to get, so I think there should be something simpler and cleaner to do here. I have to get into more details on what's going on LightGraph. So VertexStaticGraphs, we don't need all that. And we return G and SRC of E. We could inline it, but it doesn't bring much here. Alright, I think we're good now. Nope, not yet. SRC not defined. Did I? Oh, yes, of course. I even have an error that I completely ignored here. Why? Okay, getting there, I guess. Has edge Vertices not defined, of course. Edge interface 19. And same thing below. So I do like how Visual Studio Code is working in general. There's just a few things that are annoying. I think if I keep Control, is it Alt too long? Or maybe both, then it switches, yes, to the file system or something, or to the tabs on top. Very in simple. Wait, how is that an error? Yes. Okay. Oh, okay. Yeah. No, this is. It's supposed to be wrong. So. Did I not say it was wrong? Oh, yes, this is not supposed to be the case. So this is fine, this is an error. And I think we're getting there now. Yes, perfect, our tests are passing. Okay, so we now have everything for free, so the edges and so on. So lots of things are coming for free with the whole abstract simple graph subtype, which is defining lots of things that abstract graphs don't have. That's great. So one thing we might want to do is, since we're using simple graph all the way through, we might want to use them in our tests too. Simple graph. So one thing we could do is just widely copy the thing. No, we're not interested in these things, I think. Yeah, we might want to add some is valid simple graph. So thing is, what do we want to test? I'm not sure this is the best test, in fact. Should we maybe test something else? Oops. Like, test community with our thing. This is testing the algorithm, not the implementation of the graph itself. Yes, so I think still digraph. Oh, okay, this is creating random graphs. No, we're not testing the string representation of our thing. Collection operations. Yeah, that could be useful. How is it called, this thing? No, that's something good. So what are GA and GB here? Graph with at least 10 nodes and let's say random edges. No, with exactly 10 nodes, let's say. So GA is these two simple graph, no, DGA and DGB. Static graph of int val int, let's say 10 and false. So that's GB, which is roughly the same, and then what is it? I don't know why it's just getting things back together here. DGA and DGB, it's the same thing with true. Okay, and then so we have to insert roughly 20 edges in each of them. So we're not gonna get 20 edges, but we're just gonna sample a source and destination 1 to 10, and destination is gonna be 1 to 10 too. One thing we should do is maybe set a seed before that. Yeah, it might be an idea. So we need random in our test. Random, and then here, I don't get how this is, how am I doing? Seed 33. Random. Okay, so for maximum inserting 20 edges, and then add edge to GA. Well, they're not supposed to be the same graph. How stupid. GASD, GB, BGASD. Okay. And then resampling with the bees. Okay. So we're not testing the length or anything. This all looks fine. Let's run the test again, check all the lines, but it sounds roughly sensible. Oh no. So, inferred. Oh no, it's not supposed to be the same. Okay, no. It's reproducing the same thing, so. Okay. So, and after resetting the seed, we do the same thing with the bees. Just to check that the A's and the A and B should be the same for both directed and undirected. Okay, so A, and B. Okay. What are we getting into? Simple edge not defined, of course. Oh. Import from LightGraph. That's simple graph. Simple edge. So this is also testing at infer is testing that our implementation are type stable. So that's great. We now have things roughly in place. So these tests here are fairly interesting. These ones you can also take. It's roughly what we already have, but we're not doing that. So that was said this will be a set simple graphs test suite. So iterative protocol should be fine. So here this will be a static graph of so int 10 false, and below this will be true. Membership operations. Oh, we're using the fancy mathematical in and not in. The big advantage that you can use this one in line, as an operator. So left member, operator, right member, instead of calling them like a function. As an edge, yes, okay, this all looks fine. Alright, let's test this. We didn't assume at any point that we had that simple graph or anything. Okay, perfect. Oh wow, that's quite some test. So we now have a good test suite, and I think we can stop there for now. Maybe we'll just add a README and a bit of documentation, make it nice. Documentation doesn't need much because it's basically the same thing as LightGraph. Oh nice, we already have Code Cove and Travis in place. Which one is it using? Let's add 1.3 here. And in the README, VertexStaticGraph. Graphs with static fixed number vertices and very number of edges. The adjacency list is stored using S vector and S vector from static arrays.jl. I guess we'll add the address. It's Julia arrays, static arrays.jl. One notable, yes, difference from LightGraph. The simple graph is that the directedness is stored as a type parameter. All right. Yeah, maybe this could be. We could take this and put it as the docstring of the type itself. This is the only thing we need. Yeah, in the documentation, we should not worry about the implementation detail of how the back adjacency list is stored. This should not be exposed to the user. Graph, LightGraph. Graph course invariant number of edges. That we don't care. Using an S vector, that we do care. And then T is integer type, and the number of vertices, and D is the directness. Okay, let's some proper formatting of a markdown here, and then maybe a comment on the constructor, or we can put that here. Examples. Actually, but we can just use the tests here as an example. We use the constructor to show how to use it. Here, this helps a lot to indicate what the REPL is supposed to do. One last thing we can add is, if we don't have any type parameter provided, we can assume that it's going to be int. And if we have something here, 2 provided, and then D, we can assume int. Alright, so I think that's it. It was already very long, so I'm gonna stop there. And yeah, we now have a new graph type.